Good morning. Thank you for your patience. I have a few announcements before we get going. The first is that Sam's office hours are now, are 5 p.m., so it's on the updated version of the syllabus, which is online. Sam's office Thursday at 5 p.m. in the SME atrium. Mickey's office hours still, as was listed on the syllabus, Wednesday at 11 a.m. in the SME atrium. My office hour will be Fridays 3 to 4 in this building, room 207, center 207. Any administrative questions before we get going? Keeping in mind that I already explained why we're still in this room. Okay. All right, was everybody able to watch the part of the lecture that kind of went over time on molecular weight, the difference between number average and weight average molecular weight? Okay, thank you for giving me the latitude to go over my time by 8 minutes on the video, but at least it's on the video. You can watch it as many times as you want. So today we're going to talk about size and shape of polymers, and particularly how the rotational freedom or lack of rotational freedom accounts for how large or small a polymer globule is in solution. So if you take a polymer and we draw it just as an extended structure, it really doesn't exist as an extended structure in solution. When you dissolve a polymer, it kind of balls up like a sphere with a characteristic radius called the radius of gyration, which is the root mean squared distance of the center of mass of the blob to an average monomer in the polymer chain. We'll go over that in more detail as we go on. But what I'm going to do now is kind of just show you the basics of how we think about bond rotations within polymer molecules and how that affects the size. So. Size and shape. This is polyethylene. And polyethylene is just the polymerization of ethylene, which is 2 carbon atoms and a double bond in between, so C2H4. Polyethylene is just the zigzag. It's the simplest possible polymer. And of course, it looks flexible, but in reality, we have bonds that are hanging off of the carbon atoms, because remember, each carbon atom, sorry about that, will be in that room on Monday. The people in there now didn't get the memo. Not their fault, not my fault, not the professor's fault, UCSD's fault. So this is polyethylene. And because we know that nobody in here, by the way, is expecting to hear about whatever they teach in the class that we displaced, are they? Okay. Okay, so each carbon atom is attached to 4 other things. And if it's not attached to another carbon atom, it's attached to hydrogen atoms. And we never draw the hydrogen atoms, but we're going to draw them today because I want to prove a point. And this motif, it just repeats along the entire chain. Does anyone remember what the angle between carbon atoms is in a tetrahedron? 109.5. Awesome. 109.5. Okay, how about the carbon-carbon bond length? I'll take short. .5 angstroms, or 0.15 nanometers. And if you look at how these molecules pack in the solid state, and this could be the material that makes up a wax candle, for example, or it could be if you froze a sample of octane or something, you would get approximately a cylinder of with diameter 0.3 nanometers, and this is the van der Waals diameter. So for example, in candle wax, when these paraffinic chains, paraffin wax chains, which is just short molecular weight polyethylene, which is what a candle is, and unless it's a beeswax candle, almost the same thing, but not quite, and you stack these things like logs, then the center-to-center distance is 0.3 nanometers. All right, so this is the thermodynamically favored state where the molecules are in a long, extended chain, and it minimizes unfavorable interactions of hydrogen atoms bumping into each other, carbon atoms bumping into each other if the molecule were kind of scrunched up. This is the thermodynamically favored state. But what are the odds that this is the state that's going to exist in solution? That this is the conformation that exists in solution, where the molecule is just like this? Pretty low, because these bonds can rotate. So the odds that you have this state, which happens to be the most thermodynamically stable, the odds that it actually exists like this are quite low. So this is thermodynamically favored. But statistically improbable. And to see why this is thermodynamically favored but statistically improbable, or we'll get to the thermodynamically stable part first and then the statistically improbable form. Imagine that we're just taking 1, 2, 3, 4 parts of this, 4 carbon atoms worth, and that's going to be butane. So butane is just that. So this is butane. And what we're going to do is draw butane as we rotate this bond around, and we're going to see what interactions form with the other atoms that are hanging off of the polymer chain. So let's imagine that the carbon atom at the end is sticking out of the plane of the board, and it can rotate through an angle phi called the dihedral angle. And if you put your eyeball, those are eyelashes. You put your eyeball like this, and you look along the plane of the board, and this bond is pointed out of the plane of the board. What does this look like in terms of a projection down this central carbon-carbon bond? And what you end up with is a peace symbol, man, where this is the dihedral angle. And does everybody see how we get from here to here, looking along this bond? And the CH3 group in the back is pointed out of the board and is farther away from us, so that's the perspective. This is called a staggered conformation. And this interaction here between these two methyl groups is called a gauche interaction, which is somewhat unfavorable. Why is it somewhat unfavorable? The steric hindrance. So sterically, there's too much bulk in these CH3 groups, and the electron clouds start to interact through space. Now, why is that bad? Because of the Pauli exclusion principle, which says that fermions, of which electrons are a member of the family, can't occupy the same physical space and have the same for quantum numbers. And there's a huge repulsive interaction that occurs when you get to atoms and molecules too close together. It's why I can't punch through this table, because Pauli exclusion told me that I can't. Yeah?
Okay, so how exactly do you get the staggered conformation diagram made?
So what you do is we're living in this two-dimensional plane of the chalkboard, and we're looking at this bond pointing up, and this here is this bond is this CH3 group in front, and then through the board there's a bond, which is the central bond around which we're rotating, which is this bond, and the methyl group in the back, which is oriented 60 degrees out of the plane of the board, is the one in the back. Question?
Is van der Waal diameter the diameter at which a van der Waal interaction can happen for that specific compound?
The van der Waals diameter is the packing distance in a solid material, is the equilibrium separation between molecules in a solid. Did that answer the question?
Yes.
Okay. If you still have a molecular model kit from general chemistry, if you didn't sell it back to the bookstore, if maybe you never got it, or you could buy one on eBay for like 2 cents. That's actually helpful in determining these three-dimensional manipulations of these molecules. But what we're going to do is rotate this bond a little bit farther away. So we're going to rotate it another 60 degrees. And what we get then, I'm not going to, because it doesn't determine the equilibrium conformations, but what you get is this directly behind this, and that's called an eclipsed conformation. And it's transient. You only ever go through the eclipsed conformations because they're so unfavorable that the molecules don't live there for very long. Now we move another 60-degree increment, and we get this conformation, which is another staggered conformation, but there are no gauche interactions between the methyl groups. So this one is the most favorable conformation. This is so also staggered. And this one is called anti, or Sometimes it's called trans because they're trans opposite from each other. Then we have another eclipsed conformation, and finally we have another staggered gauche conformation. I'm sorry you guys in the front row can't see it, so I'm going to describe it to you. So what we have is this, except this methyl group is over here. And this is another staggered gauche. So the staggered refers to the fact that we have the groups oriented 60 degrees apart from each other, and the gauche has to do with the fact that we have this unfavorable interaction between the two largest groups that are sticking out of the projection. These things here, that's the worst bracket I've ever made. It looks like a plumbus. These are called Newman projections. Newman's own projections. Yep.
I'm just trying to understand. It's pretty clear why the eclipse conformations are unfavorable, but I noticed you didn't even consider one where the methyl groups are eclipsing each other. Is that because it's so unfavorable that it never eclipses?
Oh, we're gonna draw that one. Yes. So what I'm gonna do is represent the potential energy landscape of all of these conformations on a plot. So we will draw delta G, the Gibbs free energy in kilojoules per mole as a function of the dihedral angle phi. In increments of 60 degrees. And we'll go from 4 kilojoules per mole to 16. And we start out with the 0 degree dihedral angle, which is where the methyl groups are exactly behind each other. And if we draw butane like that in 2 dimensions, that's what it looks like. So this gives you the Newman projection where the CH3 groups are exactly front and back from each other. And we start out at a very high potential energy. Then we go down to about 4 kilojoules per mole, which is our staggered conformation with the gauche interaction. Then our eclipsed conformation that looks in 2 dimensions kind of like this is about, say, 13 or 14 kilojoules per mole. And then because these are delta Gs, these are just the changes, lowest energy conformation is going to be the staggered anti-conformation, which looks like this in 2 dimensions, and then the rest of the curve is symmetric. And the wedges just mean that the bond is going into the plane of the board. Okay. So far, so good? Yep.
So staggering occurs when you put this in a solution?
Anytime. Even if you had butane vapor or butane in a lighter, butane in a cigarette lighter is just this, or candle lighter or whatever, is just this.
And delta G is the difference in energy of two different, I guess, configurations.
So delta G is the change in potential energy as you rotate the bond around. So in this case, the change in potential energy is derived ultimately from the fact that electrons don't want to get too close to each other and they repel because of Pauli exclusion. You can have lots of different origins of the free energy, and it could be because of electrostatic interactions, van der Waals interactions. Delta G is also determined by the change in entropy of a system, which becomes very important a little bit today, but definitely later in the course.
So it might help us to think about the staggered anti-conformation as like a ground state.
I don't want to use ground state because it's so tied up with electronic and vibrational terminology, like spectroscopic terminology. But let's say that it's the lowest energy state. It's kind of like when you're on the couch and you don't want to get up. It's the low energy state. Okay, now this has profound consequences for the sizes and shapes of molecules. Even though this one is slightly lower than the two gauche staggered conformations, these conformations are still populated to a significant extent at room temperature, or actually any finite temperature. So let's say, suppose you have 3 discrete conformations. So you have 2 gauche and 1 anti or trans conformation, and you have a system with 100,000 or 10,000 carbon atoms. Your total conformations are 3 to the 10,000. Only one of which is all trans. Okay, so while we draw these structures as linear chains because it's convenient to do so, it is highly improbable that any molecule in a system will be in that single conformation, even though it has the lowest energy. It's the one that's most firmly planted on the couch that will never leave. Yeah.
This isn't really counting for the probability of any given state, right? This is just if all things created equal, we just had a random arrangement of...
We'll get to the probability right now. Interestingly, you can induce scenarios in which the chains are aligned in a polymer sample. And how do you how do you do that? You can't make them completely aligned, but if you take a rubber band, which could be like butyl rubber or something, latex glove, which is polyisoprene, and you stretch it out and you stretch out all those bonds, you're actually aligning the chains as you stretch them. So what's the restoring force? What's the origin of the restoring force that wants to collapse that rubber band back to its equilibrium state? It's actually entropy. It's the fact that you're making the chains occupy improbable states that they wouldn't want to occupy under their own free will. So their desire, in a way, to be statistically distributed among all possible conformations, most of which are more globular than spread out, that produces a restoring force on a rubber band. So sometimes you call rubber bands entropic springs because you're not really changing the intermolecular forces, at least at small strains. What you're doing is you're making the system statistically improbable, and it wants to become more probable. Of course, nothing really wants to occur. It's just what does occur. Whoa. We can calculate the ratio of trans to gauche states by a ratio of a Boltzmann distribution. So you have the ratio of the number of gauche states to the number of trans states equals 2 times a Boltzmann factor of e to the minus delta E divided by kT, where K is the Boltzmann constant, and it has a value of 1.38 times 10 to the minus 23 joules per Kelvin. Anyone know where the Boltzmann constant comes from? It's the universal gas constant. Oh, sorry, I didn't give anyone a chance to respond. The universal gas constant divided by Avogadro's number. When you see K's in equations, you're talking about molecules. When you see R's in equations, you're talking about moles of molecules. And you can usually tell because one has something to the minus 23 and something else has units of to the plus 23. So the Boltzmann constant, delta E is the energy distance between the minima. Energy difference between, let's say, between the two states. And I wish I had those boards that moved up and down so that I could still have the potential energy landscape written here. Of course, the bad news is that once per quarter I smash my finger in those things. So maybe it's not so bad. But if you imagine the potential energy landscapes, what we're looking at, what delta epsilon is the difference between the minima of the anti, which was in the middle, and the two gauche states, which were on the sides. And T is always the absolute temperature in units of Kelvin. Why do we have a 2 here? Because there are 2 gauche states per every trans state, trans or anti-state. So let's just do some quick arithmetic here to show you what these ratios look like at different temperatures. So for polyethylene, and I may abbreviate this by its recycling symbol, PE, in the future. So PE, polyethylene, good abbreviation to know. We have a delta epsilon from trans to gauche of 3.34 kilojoules per mole, and always be careful of the units. So just so you have it in your notes, K times Avogadro's number equals R, which is 8.31 joules per mole Kelvin. And if we plot, or not plot, if we tabulate the temperature as a function of the temperature versus the number of gauche divided by the number of trans, so the ratio of gauche to trans states, and we have 100 Kelvin, so very cold. The ratio is 0.036. At equilibrium. At 200, we're going to start sampling. So remember from probably general chemistry, as you increase the temperature, your distribution of occupied states tends to go from tall and narrow to short and wide. So you occupy more and more states, the greater the temperature is. So we're going to occupy more of these states as we increase the temperature, more of the gauche states, because you have more energy to occupy states that have conformations that have greater energies. And 300, so we go from 0.036 to 0.264 to 0.524. Now, as we increase the number of gauche states, the ratio of gauche to trans states, what happens to the size of the polymer blob in, say, the liquid phase? Does it get bigger or smaller? It's funny how these questions kind of follow a distribution like that. It probably goes along with the sourness of my face as I hear the incorrect answer. The intuitive answer, of course, is that it gets bigger because everything gets bigger with temperature, but the intuitive answer is wrong in this case. You have more gauche states. Remember, the trans states are the extended states. The gauche states are the ones that allow the polymer to fold back on itself ultimately, the ones that allow the polymer to fold. So if you have more folds, more ability to fold the chain in solution or in the liquid phase, then statistically the blob will get smaller as you increase the temperature because you're populating more of the states, more of the conformational states that allow bending of the chain. So this is more cheeseburgers, more coiled, smaller ball. Or blob, or other globule, other equally, I guess globule is the scientific term. Okay, a little note about nomenclature. I've been calling these conformations, which are different from configurations. So, conformation are states achieved by rotation of bonds. Yeah.
Actually, I have a previous section.
Mm-hmm.
I, or in increases in temperature, I believe. And you just said earlier that when you do that, you like kind of stretch out the polymer and like change them back into trans states because it's being stretched out. If the number of gauche states increases as temperature increases, then why does the temperature increase for a stretched out reactor?
That's a really good point. The reason you have heat going into and out of the system is because you're no longer in the entropic spring regime. The longer answer I'll get to later in the course. Is that okay? Or we'll send an email to the class. That's a really good point. Okay, conformation. So conformation are states achieved by rotation of bonds, and configuration are structures achieved by breaking and reformation of bonds. So to get to your question slightly, I wouldn't use the delta H as meaning the temperature of a system. So when you break bonds or you disassociate van der Waals bonds, you take in heat energy, and when you form them, you emit heat or energy. But let me send an email. This is butadiene. So CH2 group, CH2 group, H here, carbon atom, 2 H's here. When we polymerize butadiene, we can get 2 different configurations. This is the all cis butadiene. And if you change the catalyst, you get the all trans butadiene. Unlike single bonds, double bonds are locked into position and can't rotate unless you actually break one of the bonds. So this represents a difference in configuration as opposed to a difference in conformation. Because in order for these bonds to rotate into the trans form, you have to break a double bond. So this is a bit different from what we were talking about with polyethylene. Is that okay? These are differences in configuration, not conformation. Okay, just to complete this thought, butadiene and natural rubber, which is this molecule, which is cis polyisoprene, which is natural rubber or latex. These compounds can are all used, for example, to form, well, latex gloves, butyl rubber gloves, but also tires. So if you cross-link these materials with sulfur, that's called vulcanization. Live long and prosper. If you vulcanize the rubber in the presence of carbon black particles, then you make something that's tough and hard rubber like tires. And if you walk on the street with your bare feet and you get the carbon black on your feet, supposedly it causes cancer, I don't know. Okay, in the 5 minutes left, I want to introduce a couple of just a little bit more chemistry. This is stuff that I actually already recorded on the primer on organic structures. But since that was optional, I want to make sure that you've all seen it here. So organic functional groups are groups in polymers that fit together like Legos to make long chains. So this one, which has a nitrogen atom, is called an amine. This ROH. R is a variable in chemistry language. R can be anything. It could be usually a hydrocarbon chain, usually some carbon-containing thing, but not always, but almost always. The OH is called a hydroxyl or alcohol. And together these things are called nucleophiles. Which means that they have partial negative charges due to the lone pairs on the nitrogen and the oxygen that are attracted to nuclei, which are positively charged. Now, how about some electrophiles? So the other end of the Lego brick. This is called a carboxylic acid. The other one you're going to see in polymer science is the acid or acyl chloride. And these are electrophiles. These things combine like Legos. So Legos have holes and pegs, and they get polymerized together by stacking them one on top of each other. The same thing pretty much works for polymers. So if you add an amine to a carboxylic acid or acid chloride is more reactive than the carboxylic acid. Carboxylic acid, you usually have to heat it up and remove water as it reacts. And what you get you get an amide. As in nylon, or a peptide, as in a protein. Peptide is just the biochemist's word for amide. Or you can get something like this if you're adding a hydroxyl to a carboxylic acid or an acid chloride under the right conditions. You get something called an ester, as in polyester. And some more, slightly more complicated ones. Something that is an amide on one side and an ester on the other side is called a urethane. Urethane in polymer language, or carbamate in chemistry language. Because urethane in chemistry means something different. It means specifically ethyl carbamate. But when we say polyurethane, like a bowling ball, we're talking about a polymer made of this linkage. And the last one that I want to mention is something that's an ester on both sides of the C double bond O. And this is called a carbonate. Like my eyeglasses are polycarbonate. And together, these structures form, so these are all the linkages. So you have the nucleophile, the electrophile, and these are the linkages. And they form along the polymer chain in certain types of polymers. Generally, these are polymers that follow what are called step growth kinetics, which we'll talk about on Monday. And that is to differentiate them from chain growth kinetics. So step growth, they grow like this. Chain growth, they grow one at a time. We'll talk more about that on Monday. Thank you very much for your attention. Have a good weekend.
We have class in